Chapter 13 is all about rotational dynamics, and to understand this, we really need a rotational equivalent of force, which is going to be something we call torque. This curly T stands for tau, that's the rotational force, and it's equal to a radius times a force times the sine of the angle between the radius and force. So what does that actually look like? Imagine I'm trying to open a door. Here I've got my hinge, my axis of rotation, and here I've got my doorknob. So I'm applying a force to open this door. Let's imagine I push on the doorknob and my force kind of acts at an angle. So I'm not pushing directly, I'm pushing kind of at some slant. Now I'm pushing at some distance from my axis of rotation. I'm some distance away. That distance is the radius where I apply my force. And then the only force that's actually going to make this door rotate is this door is going to rotate about that axis of rotation. The only force that's responsible for some rotation is actually the force that acts perpendicular to my radius. So it's going to be Fy. If I draw the angle between my radius and where my force is acting, that angle we're going to call theta, and I can see from trigonometry that Fy is equal to F times the sine of the angle. So really, Fy is the rotational force, I'm going to call it F rot, the force responsible for my rotation. Any part of the force that's acting in the same direction as my radius, in this x direction, that's not going to allow my door to rotate at all. I'm pushing along the door. The only force that gives me rotation is my Fy. My Fy is F sine theta. So that's where my rotational force comes from. So now we can understand what this R is. R is the radius, the distance from your pivot point. And F sine theta is the amount of the force that you're applying that's in the direction that will allow you to rotate. So our general equation for torque, tau equals R sine F times sine of theta. Final note about torque for the moment, the units of torque are going to be equal to the units of the radius times the units of force times the units of sine of theta. Angle is dimensionless, has no units, so we don't need to worry about that. The units of radius are meters. The units of force are newtons. So the units of torque are newtons times meters. So what other things can we do with torque, with rotational dynamics? We can do work. Torques do work. So let's go back to my door and imagine I push my door open, so my door moves. My door moves some certain angle. That angular change, we've already studied changes in position for angles. We're going to call that d phi. This is my change in angular position. So that's how much my torque has moved my door. And by analogy with our usual equation for work, work is equal to a force times a change in position. The rotational work is going to be the rotational force, which is tau, times the change in position, times the angular change in position, since I'm rotating, which is going to be d phi. So in other words, the change in work that I apply to an object is equal to the torque times the change in angular position. Or dW is equal to R times F times sine of theta times d phi. They both say the same thing. They both say that the work that I do in making an object rotate is equal to the torque times that change in position. The rotational force times the change in position. No different than our linear values that we've already found, that we've already studied. It's just written slightly different in the terms of rotational forces. I can continue to derive all the quantities that we've already learned about. I can look at power from torque. Power is equal to a force times the velocity. We learned this way back in chapter 8. This is for things moving in lines. If I now have something that's rotating, then the power that I have from rotation is the rotational force, or the torque, times the rotational velocity. It's going to be omega. This is also equal to the change in work over the change in time. So these are all equivalent variables, all equivalent ways to think about power delivered from a rotational force. The last interesting, important things to look at, we're going to have the work-energy theorem. Work is equal to the change in kinetic energy. Well, the change in kinetic energy for a rotational object is equal to 1/2 the moment of inertia of that object, I final, times omega final squared, minus 1/2 the initial kinetic energy, I initial omega final squared. So we're just replacing the linear variables with the rotational variables for our rotational dynamics situations. There's no real new physics here. It's just learning how to work in terms of rotation. We can do the same thing with Newton's second law. F is equal to ma. Newton's second law in terms of rotational dynamics is going to be the rotational force, tau, is equal to the rotational equivalent to mass, something we call the moment of inertia, and we've learned about that, and the rotational equivalent of acceleration, alpha. Now that we've developed some of these equations by analogy with the linear equations that we already know, let's take a look at an example. So in doing this example, let's look at number 5 in chapter 13. In this example, you hold a 10-kilogram book in your hand with your arm extended horizontally in front of you. So I have this mass that I'm holding that's equal to 10 kilograms. What is the torque that the weight of this book exerts about your shoulder joint at a distance of 0.6 meters from the book? So what I want to know is the torque on my shoulder. So I'm going to draw my shoulder like a pivot point. My arm pivots around my shoulder, and I'm holding this book in my hand. Clearly I have very skinny arms, and I can direct what force is actually pulling this book down that's going to make my arm rotate, or at least try to make my arm rotate. That's going to be the force of gravity. The force of gravity is equal to the mass of the book times the acceleration due to gravity. This book is a distance away from my pivot point. It's a distance r. And that r, as given in the problem, is equal to 0.6 meters. So what is the torque? The torque, tau, is equal to r times f times the sine of the angle between the two variables, between the radius and the force. So my tau is equal to r times my force, which is mass times the acceleration due to gravity, the force of gravity acting on the book, times the sine of the angle between the two. I can see gravity is acting straight down, my radius is acting directly horizontal, so my angle, my theta, is going to be 90, and sine of 90 is going to become 1. So I have the torque is r times m times g. And I'm going to just plug my numbers in. Just plug and chug. The radius is 0.60 meters. My mass is 10 kilograms. And my acceleration due to gravity is 9.8 meters per second squared. I can multiply all these numbers out in my calculator, and I will find that the torque is 58.8 newtons times meters. Problem done. continuing on with learning more variables, more ways we can study angular motion, let's look at angular momentum. Regular momentum, P, is equal to mass times velocity. Now we can do angular momentum. Instead of P, we label it with an L, and that's equal to the angular mass, which is the moment of inertia, times the angular rotation, omega. And correspondingly, we can think about it in terms of calculus, where the force is equal to the change in momentum divided by the change in time, except in this case, our rotational force is tau, is equal to the rotational angular momentum, dl. Remember, instead of P, we use L for angular momentum with respect to time. Now, if no external torques are acting, in the absence of any rotational forces, then we know tau is equal to 0. So the change in angular momentum, dl dt, is also equal to 0, which means that L has to be constant. The derivative of a constant is the only way you can get 0 when you differentiate. So that gives us conservation of angular momentum as well. The initial angular momentum in a system is equal to the final angular momentum in a system, as long as you don't add in any external sources of torques. Now here's where things maybe get a little confusing. We've already discussed some rotational forces, and in particular, we talked about centripetal force. So this is a force that's acting in a circle. We derived an equation for this. We found that the centripetal force is equal to mass times velocity squared divided by r. So how does this relate to these rotational force, these torques? If we look at the rotational force, let's say I have an object and it's swinging around in a circle, it's got some velocity in a circle, and the rotational force acts towards the middle. Let's look really closely at what this situation is giving us. The radius of my circle, I'm going to draw in red. There's my radius. So what's the torque that the centripetal force exerts on this circle, on this situation with an object moving in a circle? The torque is equal to the radius times the centripetal force times the sine of the angle between the two. If I look very closely here, I can see that the force and the radius are acting at 180 degrees to each other. Force is acting down, the radius is acting outwards. The sine of 180 is 0. So my torque for centripetal force is equal to 0. There is no torque. For this object rotating around in a circle. That doesn't mean, however, that I don't have angular momentum. All it means is the angular momentum of this object moving due to a centripetal force, the angular momentum is constant. So angular momentum of a circular orbit is constant. My definition for angular momentum, L equals I omega, where I is some object in general is typically mr squared, and omega is equal to v over r, both from previous chapters. And we can plug and chug these values in. Plug and chug my I, plug and chug my omega, and I find that my angular momentum for an object subject to a centripetal force is equal to m times r squared times v over r. I can cancel one r up top with my r down bottom, and I find that the angular momentum due to a centripetal force is equal to m times r times v. Again, this is angular momentum of a centripetal force or a circular orbit. So let's do a little example involving angular momentum. Let's do number 56 in chapter 13. In this problem, we are told, what is the angular momentum of a Frisbee spinning at 20 revolutions per second about its axis of symmetry? Treat the Frisbee as a uniform disk of mass 200 grams and radius 15 centimeters. So right away I identify what I know. I know that the angular velocity, omega, is equal to 20 revolutions per second. And my first order of business is to convert this into the SI system, where 1 revolution is equivalent to 2 pi radians, and I can convert this into radians per second. So my revolutions cancel, and I end up with 126 radians per second. So that's how fast my Frisbee is spinning. I'm told the mass of my Frisbee is equal to 200 grams. And I will go ahead and write that into scientific notation right away. So that's 0.20 kilograms. And I'm told the radius of my Frisbee is equal to 15 centimeters. And then once again, convert that into SI units. That's going to be 0.15 meters. I'm asked to find the angular momentum. Angular momentum L is equal to rotational mass, also known as the moment of inertia, times omega. I am told to treat my Frisbee as a disk, so I need the moment of inertia of a disk. I can go back to my table from chapter 12 to find my moment of inertia is equal to 1/2 mass times radius squared. So I plug this into my equation. I find L, angular momentum, is equal to 1/2 m times r squared times omega. At this point, we're going to plug in our numbers. We find L equal to 1/2 my mass of 0.2 kilograms, my radius of 0.15 meters squared, and my omega, my angular velocity of 126 radians per second. And we plug and chug all of our numbers in, and we find an angular momentum equal to 0.28 newtons times meters. The final key part of this chapter is to discuss tau and L, the torque and the angular momentum, in terms of their vector nature. Both of these are vectors. Force is a vector. Momentum is a vector. Tau is a vector. L is a vector. This all means that they all have magnitude, which we know how to calculate already, but they all also have direction. So how do we find the directions for rotational forces? How do we find the direction for tau and the direction for angular momentum? That's going to require use of this wonderful right-hand rule, which we've already learned a little bit about. This turns up in cases where the rotation axis changes direction. If you've ever seen a top spinning and the top starts to wobble, that rotation axis is changing direction. So we need to know how to account for this when we're working with torques and angular momentum. So the way we do this is we define torque as equal to R crossed into F. So this is the cross product, that mathematical definition that we learned way back in chapter 2, and we treat L as equal to R crossed into P. So we do a cross product, and we get our direction from the right-hand rule. We'll work with this a little bit in class. Again, it's hard to show the right-hand rule on a whiteboard like this. The last point that your chapter discusses is finding the angular momentum of an extended rigid body. So the way you do this is very, very simple. Let's say you have a ring that's rotating, and you want to find the angular momentum of this whole ring. You can separate it into a bunch of tiny little pieces. Piece number 1, piece number 2, piece number 3, piece number 4, etc. dot dot dot. So I can take the total angular momentum as being equal to the radius of the first little piece crossed into the momentum of the first little piece. And I'm going to take that little piece of angular momentum of this first little section, and I'm going to add to that the moment of inertia, or the angular momentum of the second little piece, plus the angular momentum of my third piece. So to get the total angular momentum of a system, you add up all the individual moments of inertia. And typically, when you do this, when you do the right-hand rule, you'll find something interesting about the angular momentum. L, the angular momentum, is typically along your rotation axis. So the angular momentum usually points in the direction along the axis that you rotate around. And we'll see this with the right-hand rule in class, and where you can really see this and really get good practice with it to see if you understand angular momentum is with example 13. This is a good example to know. I would know how to do this. I would study this very closely. In fact, if anybody studies this example, has a very good solution, and comes to me the day before class, so this would be on Wednesday, if you come to my office at some point on Wednesday and show me your solution and how you solved it, I will let you solve it in class for your classmates. I'll let you describe your solution, and you can get some extra points that way. So this is going to be an extra point problem. First come, first serve, so first student to come to me with a good solution will be eligible to get those extra points by solving this problem in class. And one final example, we'll do problem 79 in chapter 13, and in this problem we're actually going to apply what we learn from example number 13 in figuring out precessional velocity. The precessional velocity, omega p, is a radius times a mass times gravity divided by angular momentum. And we're going to apply this in solving problem 79, where we have a child's toy that consists of a uniform thin disk of radius 5 centimeters. So we have a radius equal to 5 centimeters. I'm immediately going to convert that into SI units, 0.05 meters, and mass 0.15 kilograms. Mass equals 0.15 kilograms. Going to make sure I write that down. With a thin spike passing through its center. The lower part of the spike protrudes 6 centimeters from the disk. So my little spike has a radius of 6.0 centimeters. That's going to be 0.06 meters. And if you stand this top on its spike and start it spinning at a speed, omega equals 200 revolutions per second, what will be its precession frequency? So I'm going to right away, again, convert everything to SI. So I get my 1 revolution is 2 pi radians. I do my multiplication out, and I get my conversion of omega is equal to 1,257 radians per second. So now I want to visualize what's actually going on. In the problem, we're told we have a uniform thin disk of radius 5 centimeters. So I have a skinny little disk here, probably much like a Frisbee, and I have a spike that's going through the middle of it. And I'm going to start this whole thing, this whole system spinning. It's going to spin, and it's going to wobble as it spins. So as the disk rotates, this axis of rotation is actually going to wobble a little bit. That wobbling, that's what I'm trying to measure here. And that wobbling depends on the distance that I am from my rotation axis. So my disk, this disk part, How far is that from my point of rotation? What is this distance? That distance is my little r. And as we're told, our spike protrudes 6 centimeters. So this little r in my precession equation is how far I am from the point of rotation that I'm precessing around. The mass. The mass is how big my disk is, how big my object that's rotating around my rotational axis is. That's my m. My g is gravity. Gravity is going to pull this thing down. Gravity is trying to pull my disk down. That's what's causing my precession, this outside force of gravity. We can see the outside force of gravity in the terms of mg. This becomes very, very clear in example number 13. Again, you should really look at that example. And then finally, we have the angular momentum. The angular momentum of my disk is what keeps it standing up. The angular momentum of this disk right here. So I need to figure out what that angular momentum is. Angular momentum, as we've just learned, L is equal to I times omega. So now I can rewrite this equation for precession in slightly more clear terms. And we'll do that on the next slide. So reviewing from the last slide, we know we're looking for the angular precession velocity, omega p. It's equal to rmg over L. I'm plugging in my equation for my L. My L is the moment of inertia of my disk times the angular speed of my disk. I can go to my table from chapter 12 to find moment of inertia of a disk, and we find that that is equal to 1/2 mr squared. So I have my rmg again. I plug in for my moment of inertia, 1/2 mass times the radius of my disk squared times omega. I can see here that my masses are going to cancel out. So the mass of this disk really is completely inconsequential. It doesn't matter how big this disk is. And I have my precession velocity is r times g divided by 1/2 r squared times omega, how fast I'm spinning. At this point, I know all these variables. I know my little r, the distance of my rotating object from the rotation point is 0.06 meters. I know what g is. G is the acceleration due to gravity, 9.8 meters per second squared. 1/2 is just a constant. My big R squared is the radius of my big disk. The object that is actually rotating is going to be 0.05 meters, and that's going to be squared. And then my angular velocity. The speed my disk is rotating is 1257 radians per second. I plug in all my numbers, and I find my angular precession velocity, omega, is 0.37 radians per second. And just to help you out with studying your concepts, seeing if you understand these concepts of momentum and rigid body dynamics, I suggest checkups 13.1, 13.3, and 13.4. A lot of the questions in those checkups are very good for testing your conceptual understanding of Chapter 13.